In a previous video, I solved Cauchy's exponential functional equation and found all continuous functions which satisfy it. The continuous functions that solve the equation are the exponential functions b to the x, with b an arbitrary positive constant. To find the solutions, I used two methods. The first method used a transformation of the function f to reduce the equation to the linear Cauchy equation. Knowing the solution for the last equation, the inverse transformation provided the solution for the exponential equation. The second method did not use the solutions of the linear equation. Instead, using the ZQR method, I produced the solutions without any reference to any other equation. Therefore, the ZQR method is a fundamental and very useful technique. In this video, however, I will use the first technique, the transformation of the function, since my main goal is to reveal the form of the non-continuous solutions and not focus on the solution techniques. Understanding how to find non-continuous solutions of Cauchy's functional equations resulted from the work of the German mathematician Georg Hamel. The key ingredient of the solutions is what is now called Hamel basis. Therefore, to understand the solutions, we must first understand the concept of the Hamel basis for the real numbers. So, let's review the most important facts about it. Given a field f and a subfield k of f, then f can be considered as a vector space with scalars in k. In the present case, f is the field of the real numbers, and k is the subfield of the rational numbers. Hence, the real numbers can be considered as a vector space with the scalars being the rational numbers. If the set of real numbers is a vector space, there is a set of real numbers which forms a basis, and every real number can be expressed as a linear combination of the elements of the basis with the coefficients of the linear combination being rational numbers. And such is the Hamel basis. Here is the precise definition. A subset H of the real numbers is called a Hamel basis if for every real number x there exists a finite number of elements h1, h2, up to hn of the set H such that x is written in a unique way as a linear combination of these elements, with rational coefficients q1, q2, up to qn. The expression of x in terms of the basis elements is called the Hamel decomposition of the real number x. The definition of a Hamel basis does not guarantee its existence. Hamel's contribution was to prove that at least one Hamel basis exists. To do so, Hamel used the axiom of choice. Said it informally, the axiom of choice guarantees that given any collection of sets C, we can always form a set which contains a single element from each set of the collection C. The axiom of choice appears quite natural. However, it leads to certain results that some mathematicians consider paradoxical, and hence, they have argued that it should be dropped from mathematics. Despite this objection, most mathematicians accept it. Once the axiom of choice is accepted, a Hamel basis exists. For topological reasons, the Hamel basis must necessarily be uncountable. Unfortunately, there is no known explicit example of a Hamel basis. In a previous video, I showed that the most general solution f to the linear Cauchy equation is found as follows. First, we introduce a Hamel basis h in the set of real numbers. Then, we assign arbitrary values for f at the elements of the Hamel basis. Finally, we set the image of a real number x using its Hamel decomposition and the following rule. The continuous solutions are a subset of these solutions. A solution of the Cauchy linear equation is continuous if and only if there exists a real number c such that each element h of the Hamel basis is mapped to c times h. Now, we proceed to find the non-continuous solutions of the exponential Cauchy functional equation. Setting x over 2 for both x and y in Cauchy's exponential equation, we see that the function is non-negative. But the function cannot vanish at any point, since if it does, it must be identically 0. To see this, let x0 be a root of the function f. Then setting x minus x0 for x, and x0 for y in Cauchy's equation, we immediately see that f must vanish for all real values. Therefore, a non-trivial solution f is strictly positive. This allows us to introduce a transformation such that the new function g is the logarithm of f. Then, by taking the logarithm of the exponential Cauchy equation, the equation transforms to the linear Cauchy equation for the function g. But now, we know all possible solutions for g. These are found by assigning arbitrary real values of g to all elements of the Hamel basis, and for any real number x, its image g of x is set according to the Hamel decomposition of x, as has been discussed previously. Using the inverse transformation, we see that the value of f at the element h of the Hamel basis is given by the power e to the g of h. This means that values of f at the elements of the Hamel basis are arbitrary and positive. Similarly, f of x equals e to the g of x, which results to the following product of the images of the Hamel basis elements. Therefore, we have shown that the most general solution f to the exponential Cauchy equation is found by following the next three steps. Introducing a Hamel basis h in the set of real numbers. Assigning arbitrary positive values for f at the elements of the Hamel basis. Setting the image of a real number x using its Hamel decomposition and the following rule. Given what we know for the continuous solutions of Cauchy's exponential equation, we can state the following theorem immediately. A solution of the Cauchy exponential equation is continuous if and only if there exists a real positive number b, such that each element h of the Hamel basis is mapped to b to the h. And with the last statement, I have concluded this video on the most general solution of the exponential Cauchy equation. I hope you liked it. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.